My name is Alex Myers, and this is my presentation on osmotic power. We will start this presentation off with an introduction into osmotic power, followed by background information on osmosis in nature and the history of osmotic power. We will follow that with current world use of osmotic power, how osmotic energy works, membrane technology, power potential, osmotic power in Canada, the costs associated with osmotic power, the environmental impacts, and wrap it up with the conclusion and the references. Osmotic power has been under development in Europe by Norwegian company Statkraft since the 1990s. The intent is to have large-scale energy production from these hydro-osmotic power plants. These plants need to be placed where fresh water naturally flows into the sea. The basis of this type of energy production is the movement of fresh water into salt water through a semi-permeable membrane which creates pressure, which then turns a turbine. The majority of the research goes into the membrane technology because it makes up to 50 to 80% of the plant costs. This presentation presents background information and current research being carried out and looks at the potential for osmotic power as a future viable energy source. Osmosis is a natural process which takes place all the time on a cellular level in plants and animals. Osmosis occurs when water with low solute concentration moves through a semi-permeable membrane into water with a high solute concentration. A solute is simply a substance dissolved in a solution. Solute attracts water molecules to itself and are unable to pass through the membrane. Only free water molecules can pass through the membrane into a higher solute concentration. This process will continue until the solute concentration on either side of the membrane is equal. This movement of water molecules creates pressure, otherwise known as osmotic pressure. These principles are how osmotic energy uses the pressure to spin a turbine and create energy. The natural process of osmosis has been known for hundreds of years. It wasn't until 1970 when Professor Sidney Loeb took this knowledge and came up with methods on how to use osmotic pressure to create power with the use of membranes. Membranes are one of the key factors in how much energy an osmotic power plant can create. The 1980s and 90s brought more efficient membranes, which were being introduced into industrial applications. Since 1997, Statkraft, a Northern European power production company, has been taking part in the research and development into osmotic power. Also in 1997, the Kyoto Protocol was introduced, which put the pressure on countries around the world to reduce greenhouse gas emissions, which led to more renewable energies like osmotic power to become a possibility. Osmotic power gained attention in 2009 when Statkraft opened the first prototype power plant in Hurum, Norway. Statkraft is the main osmotic technology developer in the world and have made many advances in membrane tech. Currently, osmotic power plants are starting to be built all over the world as the technology becomes more viable. Current world use of osmotic power. In Europe, Statkraft, since 2009, has been testing their prototype power plant in a fjord in Norway. They would test energy outputs, but were only able to produce less than 1 watt per meter squared of power. The main obstacle is the membrane technology and lack of companies producing them. But once there are more osmotic power plants, the demand for membranes will increase. There is also another hydro-osmotic power plant set up in 2014 in Holland by Dutch researchers. It was a 50 kilowatt generating station and was built to help the country get to its goal of 14% renewable energy production by 2020. Osmotic power research in Japan started in 2009. The Kyo Wakiden Industry operates a prototype power plant with Nagasaki University and Tokyo Institute of Technology in Fukuoka. This plant differs from the European plants which use a salt gradient between river and saltwater. This plant uses concentrated salt water from a desalination plant and fresh water from a sewage treatment plant. first research into osmotic power in Canada took place from 2012 to 2013, with a study into the feasibility of setting up osmotic power plants in the province of Quebec. Hydro-Quebec estimated within the province there were 30 large rivers that flowed into saltwater and had potential as osmotic power plant locations. The energy potential was estimated from 0.8 terawatt-hours per year to 10.5 terawatt-hours per year. The goal of Hydro-Quebec is to produce this type of power at a cost-competitive price by 2020. How osmotic energy works. For osmotic power plants to work, they must be placed in the right location where they have easy access to both fresh water and seawater, most often where large rivers flow into the ocean. There are numerous ways of turning osmosis into electricity, but pressure-retarded osmosis, or PRO, is the most common. PRO plants can be thought of as desalination plants running in reverse. Desalination plants utilize reverse osmosis, which operates against the osmotic force. The salt water and fresh water are separated by a semi-permeable membrane, which must first be filtered and pre-treated to better optimize membrane performance. Natural osmosis causes fresh water to move through the membrane to a higher salinity side. Membranes must have high water flow and salt retention capabilities. The movement of this water increases the pressure on the side of the high salinity. The increase in pressure and volumetric water flow then is used to spin a turbine, creating electricity. This can be seen in the diagram on the bottom right. Membrane technology. A semi-permeable membrane is an organic filter with extremely small holes, only allowing small molecules like water to pass through. It is estimated that half of the osmotic energy produced can be converted into electricity. The membrane used consists of one thin, non-porous layer, the diffusion skin, and at least one layer of porous material which must be designed to avoid salt buildup. Filtering the water going to the membrane and regular cleaning can allow the membrane to last up to 7 years. The efficiency and high cost of membranes has been the main factor that has slowed down the development of osmotic power plants. The ideal membrane has high water permeability, low salt permeability, low attraction to fouling substances, and must be cost-effective and be able to withstand high pressure differential between fresh water and salt water. The thin film composite membrane, or TFC, has proven to be the most effective in reaching the goal of 5 watts per meter squared. Power potential. The power potential depends on the location, just like with most renewables. The amount of usable water that can be extracted from the river also limits how much power can be harnessed. This all depends on legal regulations and ecological stability. Seasonal water flow can also change the power output. Statkraft shows that the technical energy potential in Norway is around 12 terawatt-hours per year. This could provide Norway with 10% of its power needs. It is estimated that the European potential is around 170 terawatt-hours per year, while globally the potential is estimated to be 1,655 terawatt-hours per year. There is, however, room for improvement. Increasing the water flow through the membrane also increases the energy. When the feed water and draw water are at higher temperatures, there is also an increase in energy. Temperature has an effect on water flux, water permeability, and the mass transfer coefficient. With all these improvements, osmotic power still needs to meet the desired 5 watts per meter squared to become a profitable source of energy. This will have to be achieved with the use of better membranes, high salt gradients, and optimal temperature conditions. Osmotic power is still a relatively new technology, so there's not much information on the costs associated with this technology besides Statkraft's prototype power plant. Statkraft estimated it would be cost comparable to other renewables by 2010 or 2015. This is yet to happen. Inefficient membranes still remain the highest cost and determining factor in whether an osmotic power plant is built or not. Statcraft analyzed the cost of producing osmotic energy by using hydropower plants as a basis for comparison and concluded that in the future, the price of renewable energy would make osmotic power a commercially viable option with an expected pricing to range from 50 to 100 euros per megawatt hour. Not much is known about the environmental impacts because this technology is still fairly new. It can be compared to water purification plants, which are similar and well documented. There are numerous environmental effects to consider before building an osmotic power plant. Sediment displacement, shoreline erosion, water quality from chemical and wastewater spills, local aquatic animal and plant species, and changes in flow rate and current direction are all things to consider. These impacts are still fairly minor. Osmotic power plants do not produce greenhouse gases or airborne contaminants during power production. There is minimal visual impact because they can be built mostly underground. Most rivers run into the ocean in cities and industrial areas, which means power plants could be built in these areas without affecting unspoiled land. Careful selection of where the inlet and outlet are placed can help lessen the impacts on the ecosystem. Osmotic power has the potential to provide clean, renewable energy 24 hours a day, 365 days a year. At the moment, it is still in the development stages and still fairly costly. But most renewable energies start out being very expensive, and over time, with more innovation, they become viable. As fossil fuels begin to be phased out, large-scale osmotic power could become one of the main alternatives.